In this video, we'll see what is the PSEPT, that is polyhedral skeletal electron pair theory. This theory helps you to relate the number of skeletal electron pairs. This theory is polyhedral skeletal electron pair theory. This helps you to correlate or find out the structure of a borane. If you have a borane with a formula, from the formula you know how many boron atoms are present, how many hydrogen atoms are present. So it will help you to find out the structure, that is whether the particular borane has got a closo, nido, arachno or hypho structure by finding out the number of skeletal electron pairs. Now, this can also be found so as I said, it can be used to find out the structure of borane clusters. It can also be used to find out the structure of carborane and related clusters. Now, carborane refers to a cluster, a polyhedral cluster, where apart from the boron and hydrogen atoms, you have also the carbon atoms. In essence, it is like substituting a vertex with carbon instead of boron. The number of hydrogens will, of course, be different. Now, this was, to find the skeletal electron pairs, you have a set of rules, and the rules were formulated by the scientist Wade, and hence this PSEPT is also known as the Wade's rule. Later, this rule was extended to find out the structure of transition metal clusters, and by a scientist Mingo, and the extension is known as Wade-Mingo rules. Here we need to know only about boranes, carboranes, and metallocarboranes. So we'll see how you can find out the number of skeletal electron pairs. Now, for a borane with a formula, say BNHN plus M. N plus M I have written here because for a closo or a nido, you write, for a nido you'll be writing if BNHN plus 4, that is, and if it is if it's an anion, we'll correct the formula accordingly by taking into account the number of charges. So here, if you have a structure like a borane like this, and if this has got a charge, for neutral boranes, this will be 0. Otherwise, you put a charge like P minus. Now, the total valence electrons associated with this particular borane will be 3 into N. Because each boron has got 3 valence electrons, we are putting this 3 here. So 3 into N plus the number of hydrogen atoms are N plus M, and each hydrogen has 1 electron, 1 valence electron. So we write N plus M into 1 plus the charge associated with this. So this is the total number of valence electrons. Now we know for each BH unit, for the formation of each BH bond, 2 electrons are required. So for 3N, when there are N, sorry, not 3N, when there are N boron atoms, 2N electrons will be used. Now, the remaining electrons are the framework electrons or the skeletal electrons. So, if the skeletal electrons or the framework electrons are represented as F, then you can have a formula like this. F is equal to 3N plus N plus M into 1 plus P. This minus the electrons taken for bonding, that is 2N. So this will give you the total number of framework electrons or the total number of skeletal electrons. Now, what the rule says is it is relating the skeletal electron pairs to the structure. So the number of electrons have to be converted to skeletal to the electron pairs. So what we do is we need to divide it by 2. This will give you the skeletal electron pairs. So skeletal electron pairs is F by 2. So we can put this as 3N plus N plus M into 1 plus P minus 2N, this divided by 2. Okay. Now, instead of writing this N and M, if you can also write it in terms of the boron atoms. So here, if you have for a boron cluster, you can write it as 3 into B, not 3B, 3B. That is, each boron is giving 3 electrons. So this will be the number of this B will represent the number of boron atoms plus the hydrogens plus P by 2. This way also you can write, but you have to remember that this B refers to the number of boron atoms, the hydrogen refers to the number of hydrogen atoms, and P refers to the charge. If it is for a carborane cluster, you can incorporate the carbon atoms also. So the formula for a carborane cluster will look like this: 3B. So for a carborane, F by 2 is equal to 3B plus 4C. The number of carbon atoms into 4, because 4 valence electrons are associated with carbon, plus H plus P divided by 2. This will give you the number of skeletal electron pairs for a carborane, and this will give you the number of skeletal electron pairs for a boron cluster. Now, when you calculate this and you find out that if you have a boron with N boron atoms, and you find out that the number of skeletal electron pairs is equal to N plus 1. If it is equal to N plus 1, then you call this as a closo. You say that it is a closo boron. If it is equal to N plus 2, we call this as a nidoboron. If it is N plus 3, it is an arachnoboron. If it is N plus 4, it is a hypoboron. Remember, we are correlating the skeletal electron pairs to the structure. Okay, not the vertices. So here, this way you can find out whether your boron cluster is a closo, nido, arachno, hypho. Not only boron, you can use this for carboranes and metallocarboranes. Now, when you say that, you can say that in some cases, see, a BH will have 2 electrons. Similarly, a CH, represents 3 electrons, and sorry, not that. You can see how each is substituted. So a BH minus unit is equivalent to a CH unit, taking the number of electrons. Similarly, BH is, so since this is CH, BH can be equated to carbon. Similarly, silicon, germanium, and so when substitution is, remember that it is a BH unit as a whole being substituted by a carbon, silicon, germanium, or zinc. Similarly, if there are nitrogen or phosphorus or arsenic in the framework, then that is equivalent to substituting for a BH2 unit. You need to be aware of this when we'll deal further, when we'll say further when you study about metallocarboranes. But just when you're mentioning Wade's rule, I just mentioned this. And if it is sulfur or selenium that is being substituted, then as BH3, it is like a BH3 unit is substituted. Now we'll see what what rules Wade formulated for this. What we have done in terms of the rules, or how each step is mentioned in Wade's rule. This is according to Wade's rule, the general methodology to be followed when applying Wade's rules. One is what we have done. We have determined the total number of valence electrons from the chemical formula. For boron, it is 3 electrons, 1 electron per hydrogen. When it is a carborane, 4 electrons per carbon. And subtract 2 electrons for each BH unit. That is what we have done, or CH in a carborane. Then divide the number of remaining electrons by 2 to get the number of skeletal electron pairs. Now, a cluster with n vertices and n plus 1 skeletal electron pair for bonding has a closer structure. A cluster with n minus 1 vertices and n plus 1. So here what he has said is in terms of n plus 1 skeletal electron pairs. So correspondingly, the vertices here is reduced. in what I said is a cluster with n vertices and n+2 skeletal electron pair has a nido structure. So you can either say it this way or the other way, or a cluster with n-2 vertices and n+1 skeletal electron pairs is an arachno structure, or you can say that a cluster with n vertices and n+3 skeletal electron pairs for bonding has an arachno structure. Similarly, you can say for hypho structure and also weight using this skeletal electron pair brought out a relation between the nido, arachno, and closer structures with similar skeletal electron pairs, and he obtained a diagonal relationship. See, if you look at this particular borane cluster with 6 boron atoms, this is diagonal. This diagonal relationship is with the nido structure having one vertex less than the closer structure, but this skeletal electron pair is the same. For this arachno structure also, it is the same. So here, if you look at this, in the introduction, I said when from a cluster, if one of the vertices is missing, see what happens when one of the vertices, the red one is removed here to show this. So when this boron atom is removed, these two bonds which were there from here to this, is also missing. And so here you have, if this was a closed structure, here you have the bottom part open. And here, if it was a cage-like structure, now if you look at this, it is like a nest. And here again, you have a more open structure. It's an arachno. So remember, when the vertex is being removed, here you will have the framework electrons, that will be compensated by the charge that is present on this nido structure. Okay, so there is this correlation between the closer nido arachno structures. The diagonal relationship was formulated or was proposed by Wade. In this structure, only the framework boron atoms are shown, hydrogen atoms are omitted. And also, in order to show which atom is being removed, they have in the figure, it is colored differently. The first atom that is being removed will be the red one, and again then the green. So here then you can see the red one is removed and you have a structure like this. This green one is removed and you have a structure like this. So this is all about Wade's rule. Using Wade's rule, how you can calculate to find out the structures of what the structure is, whether it is nido, arachno, or closer. We will see with further examples in the next.